When we are solving physics problems, these are essentially math problems, but they aren't simply numbers. They are math problems that are connected back to something that's real, something that exists in real life. Every number that we use is not just a regular old number, but rather it is a measurement of some physical quantity. And whenever we are taking a measurement, we have to have a unit associated with that measurement so that we know what standard was used to make that measurement. So for example, if we're measuring a distance, we need to know whether that distance is measured in meters or feet or centimeters or inches. So every measurement has to have a unit with it. We can never have a naked number. We can never have a number that's just by itself. That's math. We're looking at physics. Different folks can use different units to take measurements, and when we're trying to do calculations, we need those measurements to those units to agree with one another so that we are comparing apples to apples. It wouldn't make any sense for us to try to add feet and meters, for example. We'd want to use one or the other. And so what we need to do is to perform unit conversions to convert an equal measurement from one unit to the other in much the same way that you could convert an equal amount of currency, an equal amount of monetary value in US dollars or euros or pounds sterling or so forth. It's the same quantity, the same amount, just expressed in different forms. The same way you could measure the same distance in terms of meters or feet or centimeters, it's representing the same length or space. The way that we avoid changing the value, the way that we maintain the quantity that we are referencing is to use the railroad method. Basically, we're going to multiply by 1, and as long as we multiply by 1 each time, we're not changing the value, we're just changing the unit in which that value is expressed. So the railroad method here means that we start with our original value, and we draw a long horizontal line that's sort of reminiscent of a train track. And then we draw these vertical lines to divide it up, and each pairing here is equal to 1. So 100 centimeters and 1 meter, those are the same thing, and so that's like we're multiplying by 1. 1 inch and 2.54 centimeters, those are the same thing, and so that's like multiplying by 1. In fact, that's the definition of 1 inch is defined based on the centimeter. And so what we can do is use this method to make sure that we cancel out the units and we can see the new unit that we are left with. So this is an important process for us to use, an important process for you to demonstrate your understanding of the unit conversion process, to show how numbers get transferred from one form to the next, and once we have this set up, we can multiply across the top, multiply across the bottom to get a final numerical value. Notice here, this is the final numerical value that we get, but our last step is that if we have two significant figures to begin with, we should have two significant figures at the end. So I have this horizontal bar there to show our significant figures, and then my last step is to actually round the value to the same number of significant figures we started with. Because these are definitions, they're considered exact. There's exactly 100 centimeters in 1 meter. That's the definition of a centimeter and of a meter. And so these don't affect the value, only the original measurement does. A few special cases are for area or volume conversions. If you are talking about square meters or square inches or square centimeters, you simply square the conversion factor. If you're talking about cubic feet, you would cube the conversion factor. We also deal with rates. A rate is oftentimes a velocity. It's how fast you're going per time divided by the time that you're traveling. And so in that case, we deal with that as two steps. You'd convert the top, you'd convert the distance like we saw here, and then in a second step, you would convert the time unit in the bottom. You would convert that to the new value as well. And then again, whichever method you're using, you need to round to significant figures at the end. These are the most common conversion factors. You should know all of these. Hopefully you already know many of these. These are standard imperial units. This is the definition of an inch. This is in fact an exact quantity. This is the inch, and really the entire imperial system is defined based on the SI system. That 1 meter is 100 centimeters is 1,000 millimeters. That goes to the unit prefixes that we'll see shortly. You should be able to convert minutes to seconds to hours and the like. Again, these are all exact. Whenever we're talking about a year, you can use 365 days in a year. That would be 3 significant figures. Technically, with leap years, there's 365.25 days in a year, and in fact, that's not quite exact as well. There are more decimal places there, but this is already 5 sig figs, so that's sufficient. Also, a slug, that's the imperial unit of mass, is 14.59 kilograms. That's also not exact, but that's an estimate value. Let's see a couple quick examples here. Here we have 31 feet, and we want to convert that to centimeters. So the first thing that we'll do is to write out our 31 feet. And then we're going to draw our railroad track. The jump that we use to go from imperial and metric units is always that relationship between inches and centimeters, the definition of an inch and a centimeter. So I can see here, if I want to get from feet to metric, I'm going to have to go from feet to inches, from inches to centimeters. So I'm going to use the railroad method here. I know that that 1 foot is 12 inches. And this allows me to check that I've gotten rid of feet. I've included inches. Then I can say 1 inch is 2.54 centimeters. And again, I can check that I have canceled those out. I have gotten rid of feet, and I've gotten myself centimeters. I don't actually need the rest of that line. Now I'm going to multiply across the top and the bottom. Multiplication and division is all has the same level of precedence, so it doesn't really matter what order I do everything in. And I get my final value here. Our last step is to go back. We had 2 significant figures here to begin with. These are exact, these are exact. So I'm going to end up with 2 significant figures there as well. And I can see at the end that this is going to be 940 centimeters. I have rounded to significant figures. I've included my new unit. I have not left any naked numbers. I can do the same thing with an area or a volume measurement. Here I have a volume, 87.2 cubic inches. So again, I'm going to take that value and the idea here, when you have area or volume measurements, basically what's happening is this. We said that 1 inch is equal to 2.54 centimeters. And so if this relationship here is true, then we should be able to square both sides, and it should still be true. Squaring both sides is something we're allowed to do in mathematics. That's a normal operation. And so basically here we have 1 squared, inches squared would be 2.54 squared centimeters squared. Here, 1 squared is just 1, and so you have this relationship for inches squared is our conversion factor quantity squared. In this particular case, we want inches cubed, so it's going to be the same idea. We can say that 1 inch is 2.54 centimeters, but we don't have inches, we have inches cubed, so we have 2.54 cubed centimeters cubed. Inches cancel, and we're back to centimeters. We can take this farther. We have many more decimal places here, but we see that we start out with 3 significant figures, so we want to go several past that original 3 significant figures so that we can make sure we're not rounding prematurely. But here we are at the end. We have our 3 significant figures, so we're going to round to significant figures here as well. And we would end up here with 1,430 cubic centimeters. The last one here is a rate. Feet per second is a rate of change of position, basically how far we're going per time. We want to convert feet per second to miles per hour, and so we're going to do that in 2 different steps. We're going to do feet to miles, and we're going to do seconds to hours, and we're just going to do that as 2 separate steps. So when you do this sort of calculation, give yourself feet, And then what I do here is, here's my railroad line, and this is 47 feet per 1 second is what we're doing there. So going from feet to miles, we can say there's 5280 feet in 1 mile. And there we've done our numerator conversion. And now we have 1 second here. Technically, you'd go seconds to minutes to hours, but there are 60 seconds in 1 minute, and there are 60 minutes in 1 hour. This is a very common conversion. Basically, we don't use minutes very often. We either use seconds or hours, and so you can skip this step and say that there are 3,600 seconds in 1 hour, because that's your 60 times 60. So this is an okay value to use because it's one that we use very commonly. So here I'm going to put my 3,600 seconds in my 1 hour. And I can get rid of the rest of my railroad line there. And I end up here .045 miles per hour. I had 3 significant figures, and so I'm going to round that to significant figures there as well. This will be 32.0 miles per hour. So those are your 3 types of conversions, your sort of basic conversion from one quantity measuring some physical quantity into a different unit to measure the same quantity. You can see area and volume. It's just a matter of squaring or cubing the conversion factor that you already know. And if you have a rate, if you have multiple units there, you can just do one conversion, then do the next conversion, and so forth.